Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase induction motors. By solving this problem, we shall learn how to determine overall efficiency and shaft torque of a three-phase induction motor using approximate equivalent circuit when circuit parameters are given. A three-phase 335 bhp 2000 volts 60 Hz star-connected 6-pole squirrel cage induction motor has following per phase parameters referred to stator side, which are applicable for normal slip. R1 equals to 0.2 ohm, R2 dash equals to 0.203 ohm, X1 equals to X2S dash equals to 0.707 ohm, RC equals to 450 ohm and XM equals to 77 ohm. The rotational losses equal 4100 watts. When the motor operates at a slip of 1.5% using approximate equivalent circuit, we have to determine rotor speed, input line current and its power factor, developed torque, shaft torque, and overall efficiency. Let us first write down the given data. For stator winding, resistance per phase R1 equals to 0.2 ohm and leakage reactance per phase X1 equals to 0.707 ohm. Expression for stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.2 plus J times 0.707 ohm. For rotor winding, given resistance per phase referred to stator side R2 dash equals to 0.203 ohm and standstill leakage reactance per phase X2S dash equals to 0.707 ohm. For any value of slip S, rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 1.5%, that is equal to 0.015 per unit. Therefore, Z2 dash equals to 0.203 by 0.015 plus J times 0.707 ohm. That gives us 13.5333 plus J times 0.707 ohm. Let us now determine equivalent impedance per phase referred to stator side. ZQ equals to Z1 plus Z2 dash. Using values we get 13.7333 plus J times 1.414 ohm. This may be written in polar form as 13.806 ohm at an angle 5.8785 degree. Given line-to-line terminal voltage VL equals to 2000 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 2000 divided by root 3, that gives us 1154.7 volt. We have obtained equivalent impedance per phase referred to stator side. ZQ equals to 13.806 ohm at an angle 5.8785 degree. Let us now calculate rotor current per phase referred to stator side. I2 dash equals to ET divided by ZDQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 1154.7 at an angle 0 degree divided by 13.806 at an angle 5.8785 degree. That gives us 83.63755 ampere at an angle minus 5.8785 degree. Now we shall calculate equivalent load resistance referred to stator side. RL dash equals to 1 upon S minus 1 into R2 dash. Given per phase rotor resistance referred to stator side, R2 dash equals to 0.203 ohm and slip S equals to 0.015 per unit. Therefore, RL dash equals to 1 upon 0.015 minus 1 into 0.203. That gives us 13.33 ohm. Expression for total mechanical power developed, PM equals to 3 times I2 dash square into RL dash. Using values we get 3 into 83.63755 square into 13.33, which is approximately equal to 2,79,740 watts. Total shaft power output, PO equals to PM minus PR. Given rotational losses, PR equals to 4,100 watts. Therefore, PO equals to 2,79,740 minus 4,100. That gives us 2,75,640 watts. Let us now calculate per phase working component of no load current. IW equals to ET divided by RC. Given per phase resistance representing core losses, RC equals to 450 ohm. Therefore, IW equals to 1154.7 divided by 450, that is equal to 2.566 ampere. Per phase magnetizing component of no load current, IM equals to ET divided by XM. Given per phase magnetizing reactance, XM equals to 77 ohm. Therefore, IM equals to 1154.7 divided by 77, that is equal to 14.9961 ampere. Expression for no load current per phase, I0 equals to IW minus J times IM, that is equal to 2.566 minus J times 14.9961 ampere. We have obtained rotor current per phase referred to stator side, I2 dash equals to 83.63755 ampere at an angle minus 5.8785 degree. This may be written in Cartesian form as 83.19773 minus J times 8.5661 ampere. Applying Kirchhoff's current law at node P, we get input current per phase I1 equals to I0 plus I2 dash. Using values we get 85.76373 minus J times 23.5622 ampere. This may be written in polar form as 88.9415 ampere at an angle minus 15.3621 degree. In polar form, we can write input current per phase I1 equals to I1 at an angle minus phi1 equals to 88.9415 ampere at an angle minus 15.3621 degree. For star-connected induction motor, input current per phase equals to input line current. Let us now calculate input power factor. Cos phi 1 equals to cos of 15.3621 degree, that is equal to 0.96427 lagging. For three-phase induction motor, total input power Pin equals to √3 times VL into I1 cos phi 1. Using values we get √3 into 2000 into 88.9415 into 0.96427, which is approximately equal to 2,97,094 watts. Now we shall calculate overall efficiency of the motor. Eta equals to PO divided by Pin. We have obtained total shaft power output. PO equals to 2,75,640 watts. Therefore, eta equals to 2,75,640 divided by 2,97,094, that is equal to 0.9278 per unit or 92.78%. Given number of poles of the machine P equals to 6 and supply frequency F equals to 60 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 60 divided by 6, that gives us 1200 revolutions per minute. Expression for rotor speed Nr equals to 1 minus S times Ns. Given slip S equals to 0.015 per unit. Therefore, Nr equals to 1 minus 0.015 into 1200, that is equal to 1182 revolutions per minute. Expression for developed torque Td equals to Pm divided by 2 pi into Nr by 60. We have obtained mechanical power developed Pm equals to 2,79,740 watts. Therefore, Td equals to 2,79,740 divided by 2 pi into 1182 by 60, which is approximately equal to 2,260 Newton meter. Expression for shaft torque TSH equals to PO divided by 2 pi into Nr by 60. We have computed shaft power output. PO equals to 2,75,640 watts. Therefore, TSH equals to 2,75,640 divided by 2 pi into 1182 by 60, which is approximately equal to 2,227 Newton meter. So today we have solved one numerical problem on three-phase induction motors. By solving this problem, we have learned how to determine overall efficiency and shaft torque of a three-phase induction motor using its approximate equivalent circuit when circuit parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.